Okay, good. My name is Persaud. I'm with Reflex Photonics. Reflex Photonics is based in Montreal, Canada, and we basically make optical modules for the datacom, telecom sector, but mostly the defense and aerospace sectors where we've been focused on. In particular, our expertise is with rugged optics. What I want to talk about today is parallel optics and how that can enhance embedded systems going forward. So some of the things, again, like I mentioned, is talking about embedded optics in terms of boosting the performance for embedded systems. I'm going to look at things like rugged optics construction, because as we migrate from copper into optics, there's a lot of questions with regards to what is a rugged optics and what should people be looking for as they do these designs. I'm going to look at some of the the type of optical modules that they also have, looking also at system performance, because that's really the measure of how a system will be enhanced. There's no point in having a lot of bandwidth between systems if you have a lot of errors and you have to correct for it. Also, like I said, some of the rugged requirements, and then also look at the future of optics going forward. So some of the trends that we see in the aerospace and defense sector is there's a lot of sensors that are being deployed today, high-resolution sensors in particular, whether it's an infrared camera, a visible camera, or more importantly, what we see is the AESA, or the active electronics scanned arrays, which are very high-resolution radar systems. Those things are moving a tremendous amount of bandwidth from the sensor, feeding them back into the signal processing computers, and that's where we're seeing a lot of the need for high bandwidth and to meet swap requirements. As I mentioned before, this is what we're seeing there, the high-resolution sensor arrays. The interfaces are moving a tremendous amount of bandwidth. BAE Systems did an Argus system where they constructed a 1.8 gigapixel camera that was mounted on a UAV as an example. And this system can actually track, I think, about 32 targets in real time. But it is moving gigabits of data back from the camera head and then storing it locally as well as processing it. So we see that happening quite consistently. But the area where we're seeing a lot of interest in fiber right now is in the active electronic scanned array, or the radars. And what they're doing, and that's an example I have on the bottom there, you can see there's about, I don't know if I can, oops. I'll just go back here and point it out. But right at the antenna head here, you can see some systems are having from 1,010 elements, say in an aircraft, and then on a ground station or a ship, you can take that up to about 20,010 elements. So you can even feed that with a coax system, but then it becomes very large if you start doing that by sending the RF in an analog fashion, or what you can do is digitize the signal, and then you have very low weight going back, and also low BER coming back into the signal processing computer. Of course, one of the economic advantage of this is you see the low space, weight, and power can easily be met, so your capex is going down. And this is applicable to any kind of mobile electronics, whether it's a land vehicle, an aircraft, or even a shipborne vehicle. What we see is fiber optics is really reducing the space, weight, and the power in these systems. A lot of times also we get this response that people believe that fiber optics just isn't rugged. And today we will show that fiber optics is actually quite rugged in terms of meeting the requirement, especially with its low weight and the performance that you get. When we're looking at how this will enhance embedded systems going forward, we look at performance, we look at swapC, and we look at ruggedness, because those are the key areas that we see that are of interest to the aerospace and defense sector. With regards to performance, what we're trying to do is enhance the bandwidth of the system, so in other words, the interconnect speeds. Whether you're moving packets between blades or you're moving information from a digitized sensor. So today you can see fiber optics and the transceivers will go up to 28 gigabits per second. Now, 28 gigabits per second is not going to allow you to operate over the full industrial temperature of minus 40 to plus 85. But at 10 gigabits per second, we can easily do minus 40 to plus 85, and we can achieve bit error rates as low as 10 to the minus 15. And that is very important for systems that are moving an awful lot of data in it. Because anytime you have to do correction on errors, such as FECs, or you have to do equalization, the faster you go in speed, the more power you burn. And this is something that, as people migrate from copper to fiber optics, a lot of guys do not take into consideration what it actually takes to make that link work. So even though you can run a copper line at 10 gigabits per second across a backplane, if you're picking up 5 dB of losses in that backplane, you now have to boost your drive signal significantly, which burns power at your driver. As well, you now have to put equalizers at the receiver. You may need an FEC, and then you may need a CDR. Just to give you an example, a 4-channel CDR will easily burn up 2 watts of power. So if you're looking at 12 channels, you can go through 6 watts of power just in a CDR alone. So when you start adding the FEC on there and then looking at equalizer, there's a massive amount of power that's being able to recover that signal such that you can achieve a BER of 10 to the minus 12. And this is something that I really want to talk about to system designers, because with a fiber optic system, if you can bring the fiber relatively close to the driver, there's hardly any losses. There's no need for equalization. There's no need for you to do a fault error correction, and you do not need a CDR to recover the signal. So right off the bat, from that perspective, you save a massive amount of power by using fiber optic system when you go beyond 10 gigabits per second. So with regards to SWaP-C, the picture I show in the center there is just an example of, that's about 60 microcoax cables and the size of it. The amount of bandwidth that you're transferring over those 60 cables, you can transfer them in a small empty connector right on the side there. So like that's an empty connector. You can go up to 64 fibers within that space. And to do that with coax, that's the kind of size you're looking at. Not to mention the coax cables that have to go behind that. There's a huge penalty in terms of weight as you start to scale the performance of systems. And fiber optics is clearly a winner going forward in this case. Costs also of these systems continue to drop all the time. The transceivers are going down in cost. We're getting better at them. Ruggedness I talk about today. Reflex Photonics has fully qualified transceivers to work from minus 40 to plus 85, full 10 gigabits per second, and we achieved a 10 to the minus 12 error rates. We also go into shock and we meet a very high shock and vibration because we make a part that's surface mountable. So with the BGAs, when you attach that part onto the board, it's attached very tightly into the fact if you even want greater shock tolerance, you can even underfill it with an epoxy. So it's not coming off. It's very, very strong. Moisture, we know in aircraft you can get things like rapid decompression. So if there's any air that's available there, the air can condense and there could be some obstruction of the optics. But we've learned how to seal the optics such that that is a non-issue anymore. You can either do hermetic sealing or you can just do a potted material, but we can solve those problems. And lastly, we know fiber optics is inherently immune to EMI and nuclear radiation. And that's my picture at the bottom there showing Armageddon and the fiber optics well working in there. Okay, so rugged optics construction, as I mentioned, as people migrate from copper towards fiber optics, there's a lot of questions as to understand, well, how should I pick a transceiver? What is it that I should be looking at? Because the datacom, telecom market led the way for fiber optics, and many fiber optic transceivers, because that market is so massive, it's very cost sensitive. A lot of people design to meet the requirements of the telecom, datacom market, but that's a very controlled environment technique that they use, where you have controlled cooling environments. So if you design a transceiver for the telecom datacom and you simply migrate it to, say, a VPX application where you have very rugged or harsh environment, you've got to be very careful in terms of ensuring that the long-term reliability of that product will be met. So this is why I thought I should talk a little bit about some of the construction methods that's used within a lightable. I don't know if I got a chance when my colleague was passing around some of our products, so you might get a chance to see what a rugged construction looks like. That's a picture that's up there. But what we're looking for, the first thing that the aerospace and defense sector always asks for is a wide operating temperature range. So they need the -40 to +85 operation, and they need to have full 10G performance at it, achieving the BER of at least 10 to the -12. In fact, one of our customers recently told us that 10 to the -12 wasn't good enough. They wanted to see 10 to the -15. And that was largely because of the sheer number of fiber that was coming back from the antenna head. They just could not tolerate the error rates in their system. So we can achieve the wide temperature range. Now, the way you will achieve the wide temperature range is you have to do a design that's thermally conductive, because what you have is a laser that's very sensitive to temperature. The laser power efficiency drops as the temperature goes up. But what's worse is that as you go down in temperature, the laser response goes down. And because the laser response goes down, you can no longer achieve very high speed anymore. So while some people you can achieve 10 gigabits per second easily in a very constrained temperature range, say 0 to 70, the minute you drop below -20 degrees, your laser gets so slow that you cannot achieve the 10 gigabits per second anymore. Or if you do achieve it, you're going to incur an awful lot of errors. So this is something that when you are looking at a transceiver and someone tells you I can achieve 10 gigabits per second over that temperature range, you need to also look at what kind of BER they're really getting over that temperature range. As I said, you have to do a thermally conductive design. The other thing that's very important is that you use low CTE materials, because essentially what you've got is a laser that's been coupling into the fiber, and that coupling mechanism is aligned to within microns. So if you have high CTE materials, and when you go over the temperature, they're going to move, and you will lose a good percentage of your signal. So it's very important that you understand that low CTE materials are used, and they can withstand these high temperatures. Moisture, I mentioned, moisture and optics are not a good thing, because you can have water particles building up in the optical path. It will attenuate the signal. It will affect it. So you have to use some techniques to seal that. The two most common are a hermetic sealant, but that's an expensive approach. The other way is to just use a special material, like some kind of a silicone material or something like that, to seal the entire package up. Surface mounting type transceivers is very important for ruggedness, and the main reason for that is the surface mount. If in the case of what we're passing around, you have the BGA balls, so you can attach very securely to the board. But the other thing too, surface mount gives you, it's a low profile package. So because your center of gravity is very low, you can tolerate very high amounts of shock and vibration on that part. And what it also does is, with a surface mount device, you can actually heat sink it straight to the board, so you don't need to bolt on a big heat sink on the top of the part. When you bolt a big heat sink on top of the part, then it's not as effective or tolerant to shock and vibration. So these are the things that you really need to look at when you're designing your blades. As well, if you look at some parts that's available, they have sockets on them. And sockets are great. You can just plug them straight in. But the problem with that is the contact between the sockets is generally very small. So if you go in a high shock environment, what you might find is some chatter going on with the socket. So just to be careful with that. Now, these things, you don't see them when you're at low speeds, but when you're getting up into the 10 gigabits per second and you're looking for low error rates, these are things that you have to consider. The type of optical connector, or the method in which you connect your fiber into the transceiver is another thing. What we at Reflex Photonics wanted to do is to make a part that was fully pick and placeable, so it would be compatible with high volume electronics assembly processes. To do that, you can't have a pigtail that's attached to the part. It had to be self-contained. So what we did is we created a self-contained part with a standard MT connector on the front of it. In case you guys are not familiar, that is an MT connector, as some of the people have mentioned today. And that part is fully self-contained by itself. What that does for you in terms of having the cable not attached to it is that you have flexibility now, because now you can create a fiber optic cable and you can terminate it to whatever you like on your chassis. So whether you need a 38999 connector with individual ferrules on it, you could do that if you wish, and that can all be done in the last minute. One of the biggest complaints that I've witnessed when I go into some people who have tried to deploy fiber optic transceiver and they look at pigtail version. Pigtail sounds great because there's one less connector, so you get about a half dB savings. However, when you take it into the manufacturing guys and they assemble the part on the board and they have to wind the cables, what they often do is they crack the cables because they bend it too much. And then once they crack the cable, they have to throw out the entire assembly. That is not a good thing for manufacturing people. And I've actually had this complaint by quite a few companies that have gone with a pigtail version, which is why we have chosen not to use pigtail. It's really for manufacturability purposes. Lastly, when we look at the types of cables that are available, and to meet the low profile nature, especially when you're looking at VPX blades where it may be very compact in a in a chassis, what we didn't want to do is increase the thickness of that blade. So we've created a very simple attached cable structure, which is there. You have basically a small empty connector with some dowel pins that connects in there, and then it's a very simple clip-in structure to hold it in there. There are dowel pins built into that empty connector, so you have very good shock and vibration tolerance in that plane, and then you've got enough force from this very lightweight clip. All of this is very lightweight, so it's very tolerant to shock and vibration. So that's just a few things that one should consider as they start looking at implementing type of rugged optics into their boards. I'll talk a little bit about the type of optical modules, because that's another consideration too. You can look at standard datacom type modules, or you can look at more embedded modules. I typically classify modules as externally pluggable type modules, so things like QSFP, SFP, CFPs, and I call them externally pluggable because they are field replaceable. If you've seen an Ethernet switch as an example, what you can do is take these transceiver modules, you plug them straight in. If they go bad or they fail, you simply unplug them, put another one in. They're very cheap because they're meant for the telecom, datacom world. The telecom data world is more price sensitive. They're not so much, reliability can be managed through the network. In other words, if you get a connection failure, the network understands where the failure is. They can route around it. So it's more of a fault tolerant design by nature. So in the military area where a box may be closed, you don't have the ability to just unplug a module like that. So if we look at the top here, the top section is referring more to the embedded parallel optical transceivers, and that's where I see the defense market focus more on. There are different types of modules in there. There's the Reflex module, which is more of a surface mount component. And then you have the pluggable on the right. There is something that's been around for a while from Avago. It's called a micropod. It's used heavily in supercomputers. Again, very controlled operating environments. It has a socket on it, works really well. They've sold a gazillion of them, and they are dirt cheap. But you want to be careful about putting it into a harsh environment. The other one there that's kind of similar to the Avago would be the Firefly part, and I'm sure most of you are aware of that. The other component is this Snap 12 here. Now, Snap 12 is kind of interesting. It's been around for a long time, but if you don't want to have to deal with fiber at all, this is a fully integrated module. So you can come in with, it has a socket on the bottom, so you bring your high-speed differential lines into the bottom, and it gets converted into optics. Once you plug this in, you can just bring the MPO connector right out onto the front panel, so there's no internal fiber to deal with. It's not a very rugged, an MPO connection is not a very rugged connection, so it may not be suitable for a very harsh environment. But if you're working in a relatively benign environment, let's say, for example, a server blade, and you can support an MPO connector, then you just plug it in and bring it in, and there's no internal fiber management to deal with. Sure. Okay. System performance, as I mentioned, I talked a lot about this already. The key thing about system performance is you're looking at the BER on the link. So, and what we've seen here is really there's a 10G challenge of how do you achieve the 10 to the minus 12 as you go to 10 gigabits per second. There's a lot of parameters to affect here, but you really need to start with a very good eye. And you have to consider some of the issues with the laser response over the temperature. Just lastly, I'll talk about the future, just a couple of things. The future of embedded optics. So these are some of the things, and many of you in this forum have asked me the questions about can we have an integrated optical connector with the Vita66. So that's something that we may see come up in the future. Some guys want wider range, so minus 55 to plus 95. Lower profile parts, but it's 3 millimeters. Our part is 5 millimeters high today, but some cards are even looking for lower profile. 12 full duplex channels, so you get 12 transmit, 12 receive in the same channel. And then, of course, everybody's talking with 28G today, so we intend to go forward with that. You can get that in commercial temp. It's going to be a while for industrial. And then lastly, light on chip. Light on chip is where they're trying to bring the optical modules right next to, say, an FPGA driver, like that. Takeaways, you get high performance with parallel optics. You get less swap-C with it. I've kind of demonstrated that. It is proven. We have sold thousands of these things into the defense applications today. It's rugged and it is reliable. So essentially, we see this as giving embedded systems of the future a winning edge.